I the basic the idea behind this is you have this finite state automaton, which is the game of life, where it's a game which you start and you have a group of cells present on in some abstract space, and then you define certain rules on which these cells can interact with each other. That's what you define, and then you just watch what happens, and then you try to mathematically analyze what may or may not happen. The simple rule on which this entire thing works is, it says if you have a group of people living together in a village, what may happen, right? And you try to model that situation into just mathematical points, and you see what beautiful patterns you get. There are a lot of YouTube videos on this game of life, and you can check them out. Essentially, the entire game is defined on three simple rules. It says if you're surrounded by a few people, you're good. If you're surrounded by too many people, you can die. If you're surrounded by nobody, you can die. And if there are too many people, somebody can be born, right? These are the very simple philosophies on which John Conway built his game of life. And I will actually explain it to you in detail when I talk about the game of primes. So that way you can actually understand what I tried to do. And recently, I was able to write a code on Mathematica to actually run this beautiful simulation. This code may be a little too long to actually get into, so we'll just run it, and I will explain to you what exactly happens. So I made a function called game of primes, and then I just run it, and it will ask me what should be the length of the game of primes. And once it runs, I will explain to you in detail what it is doing. Okay, so we have this board with us where we have all these numbers. Okay, and what we do is this is a 5 by 5 square of numbers. So I'm starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then 21, 22, 23, 24, 25. So I have numbers filled in a snake-like order. And what I say is, this is what happens. Okay, now every number is either prime or composite, except for one. And you pick any number that you want, and you look at all its neighbors. So let's say I pick the number 8. 8 has neighbors all around it. So 2 is a neighbor, 3 is a neighbor, 4 is a neighbor, 7, 14, 13, 12, and 9. These are all the neighbors because they are adjacent squares to 8. Okay, and the rule is as follows. If a number is surrounded by 3 or more prime numbers, it becomes red. Okay, and if a number is surrounded by more than 4 prime numbers, it goes back to becoming black. Okay, so this is how we define in Conway's game of life, he calls it life and death. Here I'm just calling it black and red. So and then I say that if there is a number which is red but it has no prime numbers around it, then it goes back to becoming black. These are the three simple rules. Just like how Conway defined people being surrounded by other people and things like that, I'm just talking about numbers being surrounded by other numbers. If it is surrounded by prime numbers, it becomes red. If it is surrounded by too many prime numbers, it goes back to becoming black. If it is surrounded by no prime numbers, it goes back to becoming black. So essentially what I want to do is study how prime numbers are distributed by making it into a visual game. Okay. One last rule that I added is that if a number becomes red, even if the number may be a composite number, it is treated as a prime number once it becomes red. So we will see what happens. There is a number 8. Okay, it's a composite number. It is surrounded by 2, 3, 7, and 13. So it is surrounded by at least 3 prime numbers. So in the next iteration, it becomes red. Okay. Now we look at this particular iteration. You can see 4. Why did 4 become red? Because 4 was surrounded by 3, 5, and 7. So it's surrounded by 3 primes. It became red. Why did 9 become red? Because it was surrounded by 2, 3, 11, and 13, and so on. So each of these numbers, which was black when we started the game, became red because of whatever it was surrounded by. Now what happens in the next state? You can ignore this. This is just some binary encoding that I'm doing so that the computer remembers that particular grid. I'm making it 1 if it's red and 0 if it's black. It's simple. Now in the next state, 4, which was originally red over here, goes back to becoming black because it has 1, 2, 3, and 4 different neighbors who are either red or prime. So if you have too many neighbors who are prime or red, you go back to becoming black. 3, which was black in the beginning, goes back to becoming red because now it has 1, 2, 3, 4 numbers that are red, and then it also has another prime neighbor, so it goes back to becoming red, and so on. So it's very simple. You become red or you become black based on how many red or how many prime numbers are around you, and you let the game go on. So this happens, and it goes on and on and on. Somebody here in the audience will probably think about this. Will this go on forever? Well, it won't, because we are starting with a finite number of numbers, right? We started with 25 numbers, and this is actually trivial. How to prove it doesn't go on forever? Forget all the rules that I told you, forget whatever the prime numbers and composite. If you just have 25 different numbers, and I tell you that they will randomly become black or red, but there is a pattern on how they change from one state to the other, well, there are only 25 numbers here. So we have 2 to the 25 number of different combinations. There are 2 to the 25 number of binary encodings possible. So it's a finite number, however big it may be. I think 2 to the 25 is a very big number, but it's a finite number. So eventually, by the pigeonhole principle, you will have the same state repeat. And because the rules are consistent, if you reach the same state again, then from that point on, everything happened would already have happened in the past, because you reach the state twice. So then you'll reach the next state twice, and then you'll have a cycle. So in this case, we reach a cycle after a few number of turns. So if you want to see a cycle, what I will do is I will run a shorter version of the game of primes, which is just 3 by 3. And you will see that it reaches a cycle. So I start like this, then I get this, 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 and we are in a cycle. Because the next state that would happen has already happened before. You see this state that has happened here led to this state, but then the next was this. So that state had happened in the past. So basically the thing that would happen next would be this. And then what would happen next is, again, it would be this, and they would just keep oscillating. So we reached a cycle. So this is where the mathematical aspect comes into this. And I've written a paper. It's on archive. You can read it. Although now that I look back at it, I do feel that paper is a little elementary. I wrote it a long time ago. Maybe it needs a revised edition, but I would be happy to take any comments if any of you has any suggestions. The point is, just knowing how many prime numbers there are in the beginning of the grid and running this experiment will allow you to study how numbers may interact with each other and lead to different patterns, whether it is cycles. So many interesting questions, right? You can ask, how long does it take before I reach a cycle? This didn't take 2 to the 9 or 2 to the 25. It took like 6 or 7 states. How long is a cycle? In this case, the cycle is having length 2. Will the cycle length always be even? Will it be odd? Will it be prime? How many numbers do I need in the grid to achieve a certain cycle length? And these are all wonderful combinatorics, probability, and number theory combined problems. I wanted to give this as an example because this is a completely pure math area, which is analytic number theory, which studies the distribution of primes. But you can make it computational when you make it visual and you make a game out of it. And now you can do a lot of things and you can study. In fact, me being a music buff, as a professor told you at the beginning of the seminar, I wanted to inculcate music into this as well. So what I did is I thought, okay, I will count the number of numbers that are red, and based on how many numbers there are, I will attach a musical note to it. So those of you who are musicians may know that there are 7 fundamental musical notes: sa, re, ga, ma, pa, da, ni. Or if you're doing it in the Western way, it's do, re, mi, fa, sol, la, ti. So you have 7 notes. So I said, okay, I will look at all these numbers modulo 7. And if it's 1 mod 7, I'll play the first musical note. If it's 2 mod 7, I'll play the second musical note, and so on. So each state would have a note attached to it, and you can create music. So, I mean, this has a plethora of possibilities, and there is no real end to it. This is just another way by which you can play around with numbers when you make it computational. So I do apologize if the last part was a little too fast, and I assure you that this is actually a beautiful thing. I can even share a YouTube link where I demonstrated this game in some other talk, and there, I actually go into much more detail and you can even read the paper. My thesis basically at this point for this talk is what I wanted to show you was pure mathematics and complicated branches of mathematics can look very deceiving and scary when you look at them in a very abstract sense. So one of the ways by which you make it more interactive is when you make it computational and when you make it visual. So I showed you a proof in induction by using symbolic expressions and symbolic code. I showed you a cellular automaton just by using some simple code in Mathematica, and I showed you how prime numbers can interact with each other. We were able to plot different factors of a number, and we were able to plot some geometric shapes. This is why I really feel this particular area in mathematics has a huge scope going forward, because you will have people from different interdisciplinary areas merging together. You will have people with strong computer science backgrounds, people with chemistry backgrounds, people with physics backgrounds, pure math background, data science background. You all meet together, and what you work on is writing interactive code for any area that you like. And most of these interactive codes will have a certain mathematical background to it. So any knowledge of mathematics is always useful, but there is a lot of research that can prosper when people of different backgrounds come together and work. This is very interdisciplinary and it's very diverse. It's not like a pure mathematics department where everybody is only doing proofs, or a computer science department where everybody's probably trying to do a certain coding project. This will be a good blend of the pure mathematicians and the applied mathematicians, and that can pave way for a wonderful future ahead. Thank you so much for giving me this opportunity to talk, and I hope you have fun exploring mathematics. That's a picture of me at my graduation. That was the happiest day of my life in front of the mathematics department, because I think studying mathematics and computer science was the best thing that happened to me. And I truly encourage and I wish you all a very, very bright future ahead, and be the next generation that changes the world of artificial intelligence. Thank you so much. Let's chat if you have any questions.
If anybody has a question, please go there and ask. Mike is
in your game of primes, there was a 5x5 grid. I'm sorry.
Yes, I can hear you.
It was a 5x5. And there, after the first step, the 4 that was red turned black, whereas you said that it was surrounded by primes. I didn't understand that step.
Okay, let's go back to that. Is this can you see my screen or no?
Started here.
Can you see it?
Yeah,
okay.
I can see it.
Good. So let's go to the game of primes, and let's run the 5x5 grid, and let's try to look at each state, and I will tell you what happened for every number. Let's run it. 5x5, and let's just look at the first 5 states. Okay. So why did 4 become red? 4 became red because it's surrounded by 3 primes, 3, 7, and 5. So far, so good. That's why it became red. Now, what happens in the next state is, once a number becomes red, we treat it as though it's a prime. So basically, it has the power to make other people red as well. So once it becomes red, it doesn't matter if it's 8, it's still treated like a prime number. So what happened in the next state is now 4, which is red, is actually, I use the words excited and dormant. So dormant is if it's black, excited if it's red, so that it basically kind of gets alive. So maybe that would make it easier to understand. So 4 is excited, but 4 has 2 prime neighbors and it has 2 excited neighbors. So the total is 4. And if the number of people around you is more than 3, you go back to becoming dormant. So you have primes and excited numbers together, that makes 4 go back to becoming dormant. But in the very next state, because now it has 1, 2, 3, and 4 neighbors who are either prime or excited, it goes back to becoming excited. But now, because it has 1, 2, 3, 4, 5 neighbors who are either prime or excited, it goes back to becoming black. So 4 in this case kind of oscillates. The only way 4 could remain red is if only these prime numbers were red, right? If the prime numbers are red, or if the prime numbers are black or whatever, then it could stay. But the moment either 8 or 6 becomes red, then it has a total neighbor count of 4, which are either red or prime. So you see, whenever 6 or 8 becomes red, it can change its state. And this just goes on and on and on. So this is again a very interesting thing to study as to, does a number state oscillate all the time? Because in this case, if you see, the number 1 did not oscillate because it started red, it started black, it's still black, still black, still black, and suddenly becomes red, and it's red again. So it's a little random, but I think the issue, I think the question here was basically what happened to 4. The thing is, we should also count a composite number as prime if it's red. Okay. Any other questions? Maybe we can take one more question since it's close to 10:30. I'm happy to take 2 more questions, but if you have another event coming up, we could, do one more question.
Yeah. Just come and give us mic is.
Thank you for the question. Yes, hello.
Yes. Hello. I had this question that in the game of primes, is it always necessary for the number of stages for a cycle to be found to be related to the grid? Like, for example, if it's a 3x3, does the number have to be related to
The length of the cycle or the number of states to reach the cycle?
number of states to reach the cycle?
Yeah, no, it's very random. So what happens is, for I think for a 10x10, it takes some 600 states to even reach a cycle. But for 11x11, it's much smaller. It's very random. You can see it in the paper. Actually, just give me a second. I have the paper right here. I have a table which shows you how many states it takes to reach a cycle. So let's just look at that table. I hope I do have that table. This is actually talking about the cycle length. It's not talking about the number of states to reach the cycle, but that's also random. It's both of them are random. Let's look at the cycle length. So in this case, this is the dimension of the game of primes, and this is the cycle length. I know your question was about how many states it takes, but these are kind of similar problems. They're both random. You see, the length of the cycle for 6x6 is 44, but the length of the cycle for 7x7 is just 8. And look at the length for the 12x12, it's into the 20,000s, and then it goes back to 24. So the issue here is our upper limit is very high. We know there will be a cycle. We know the length of the cycle is finite, but it's 2 to the n squared if your grid is n by n, right? So it's a huge upper bound, and it may be very random. I do have a certain theory that eventually there should be a certain monotonic nature to it, whether it's increasing or decreasing. I have a feeling at some point it should start increasing as to how long it takes to reach the cycle, but it's very difficult to say that because we don't exactly know how the prime numbers are distributed. This all depends on how the primes are distributed. We know how many primes are there, but we don't know where they are present. Like we don't know how many twin primes are there, or how many primes with a gap of 4, or how many numbers exist with 3 numbers around them that are primes. So these mysterious conjectures in number theory make this thing tough to prove as to how many, what is the length of the cycle, or how many states it takes to reach the cycle. Very good question. Very good question. Okay. Do we have one more question or?
Yeah, please.
Okay.
One more question.
Yeah, sure.
Yes. So one of the things that made Game of Life interesting for me was the emergent behavior of different things like gliders and shyness and all these things you get from such simple rules. Is there some similar emergent behavior in Game of Primes?
A couple of things I want to say about that. Maybe I won't be able to show it right now because I don't have the exact calculations for one of those. But what I did observe was I was able to get a certain combination. So there are 2 things that you can do to this game of primes to make it interesting. You don't have to make it necessarily numbers consecutively. It doesn't have to be 1, 2, 3, 4, 5, 6 or whatever. You could just say, okay, I will do 1, 3, 5, 7, 9, 11, 13, or I will do 1, 7, 13, 19, 25. So if I give gaps of 6 or gaps of 12, I have higher chances of having prime numbers there. So it may make it interesting. So you can play around with that. Another thing you can play around is what you start with. Why should you start with 1? I mean, you could start with 10 or something. So these are two things you can play around with it. And I did encounter a certain grid where it started with only one number being excited at the very top. And in the next state, I had 2, 3 numbers around it. And then I had more numbers, and it kind of spread from the very top of the grid all the way to the bottom of the grid. So I had like, it wasn't a glider, but I sort of had this monotonic increase of number of elements that are excited, and it kind of grew it was growing like that. I had another one where I had the center of the grid excited, and then it kind of was growing like a rangoli type of shape around it. It was very beautiful. One of the restrictions, though, is it's a finite grid, where the game of life is not finite. It can grow infinitely. And here I had to make it finite because it would be difficult to study what is happening with those numbers if we didn't have a limit on them. If we just let it grow, how do you even explain it? Because then the moment the game starts, you don't even have a definition of which number is which number's neighbor, because you don't have a length of the grid. So, but despite having those constraints, we do get to see these patterns when you modify the grid. If you start with these 1, 2, 3, 4, 5, that will never happen, because we have these lot of prime numbers in the first few rows that will just mess up all these things. So there is another software that I do have, not currently available with me, but maybe if you look in the paper, I think I have a link to that. Is where you can do those different modifications, and you can see more beautiful patterns, and you can even try to make it rectangles. It doesn't have to be a square. One could even think of a 3-dimensional situation, like a Rubik's cube, where instead of having 8 neighbors, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know, like 3D neighbors around you. I did have this theory where I wanted to make it 4-dimensional, where I wanted the 4th dimension to be time, where I say that there is this number can go back in time and revisit a certain state and go back to becoming excited or dormant. So there are different things we can do with it. But yeah, as of now, that pattern of one number being at the top and growing, and then a number with 1 in the middle excited and it growing, were two beautiful things that I was able to observe. Thank you.
Yeah, it's midnight over there in US, and I am sure he is taking a lot of effort for us and giving this talk. I just want you to show that picture once again for the students to have a look. Conway's picture along with you.
Okay.
We'll just take a couple of more minutes.
No problem. I am actually good, Professor. It's not too bad.
Yes.
We can talk for a few minutes.
Okay. Here you can see in the red color, he's Professor Conway, and of course he's one of the top mathematicians. You might have heard about Donald Knuth in computer science. Computer 5A, you are seeing, of course, just like number 5A, you are seeing computer 5A, you will get Knuth. Knuth is like Vishwacharya of computer science. Okay? After Knuth, only everybody else. So at least. And Professor Knuth, he used to meet very often Professor Conway. Okay, and just see, he knows the importance of math. And it so happened, a small story. Professor Conway, he told the concept idea, and he wrote while having a coffee. They wrote on the butter sheet, or what you call the wiper sheet, what you call. He wrote on that. What you call in standard term? Tissue paper. Okay. So he wrote on the tissue paper the idea, and Professor Knuth took it away, and he wrote a full book on that. It is known as surreal numbers. You can read that. Truly wonderful. So that's the level of Professor Conway. Okay, just write some few things on rough paper. That itself becomes extremely famous. Okay, so just I wanted to tell about that.
I wanted to quickly add.
Yeah.
You may not believe this, but when this picture was taken, I did not know who that person was. I did not know that he's John Conway. So what happened was I was 17 years old. I didn't know much about any of this. Maybe I was 18 years old. I was dropped at the math department by one of my friends, and I just went to the tea room, and they were having their afternoon tea, and I randomly walked up to him because he looked old and he needed some help. So I helped him get the cookies and milk. And then I asked him, say, I've come all the way from India, so I have some of my conjectures in prime numbers. Can I please discuss them with you? He said, yes, I happen to like mathematics a lot, so let's sit and chat. So then I started showing a few things on the blackboard, and he was excited that he called two of his friends. And we clicked this picture, and I had a doubt that, okay, this is at Princeton, he may be somebody famous. So just before going, I asked him, what's your name? He said it's John Conway. And then I went home and I read about him on Wikipedia. And then a year later, I attended a summer camp somewhere in Pune, and I learned about the Game of Life. So when this picture was taken, I didn't know who he was. I didn't know Game of Life. But I do look back at it as a very important moment in life, because I think I decided to pursue mathematics seriously as a major and as a PhD in mathematics on this particular day. Until then, I was very unclear, but this conversation of about 2 hours had a very major impact on my life to take it seriously and pursue it. So this Game of Primes is some sort of a way of remembering this very important day, and as a tribute to this man who inspired me without me even knowing who he was. And I actually believe that that is the reason why he ended up talking to me, because if I went to him saying, oh, you are very famous, can I have your autograph? And sometimes these people don't want to talk like that. They are tired of having media or fans or all of this. Sometimes they just want to talk to people who don't know who they are. So he thought, oh, this fool doesn't know who I am, so let me just talk to him. He won't trouble me too much. So I kind of lucked out. Maybe if I knew who he was, I may not have spoken to him naturally. So yeah, that was another the funny story behind this picture.
Yeah, this reminds me my interaction with him. Luckily, it was very similar. And what happened was, I knew him as an algebraist, but not as a person who invented a game of life. And he spoke around 1 hour. And Princeton University is something like each department, they're putting on the notice board, okay, this year's Nobel Prize winners. Okay, so that's the level of Princeton University. Departments are putting, okay, this year, these are the people who got the Nobel Prize. So it was a very nice interaction with you, Raghavendra.
Thank you, Professor. Thank you
And
so
we
much.
we hope to see you when you come over here in Manipal. Your some shows over here, and of course, definitely we will encourage students to interact with him whenever he comes down to Manipal. And please feel free to mail him. I'm sure he'll be responding if it makes some sense. Of course, anybody has any questions before we end the meeting? Anything you want to ask him?
You can ask me questions that may not have been directly linked to what I spoke about. That's also okay.
Sure. Anybody has? You can have to just come forward. If not, let's once again thank the speaker.
Thank you. Thank you, Professor, for the opportunity. It's very good to see you also.
Thank you. And we'll see you soon.
Thank you. Thank you, everybody. Have a good day. Bye-bye.